Alright, for today's episode of Physics with Mr. C, this is going to be a run-through of Unit 3. So everything you would have seen, because you have seen everything at this point. So what we're doing is run through all the concepts, vocabulary, terms, a couple of example problems. Let's go. Position, okay? Just going with basic concepts real quick. Position, our variable that we use in all of our equations is x. The unit is the meter, standard unit. Keywords that you'll see is how far, distance, and displacement. So those are the words that kind of describe position. All right, moving on. Velocity is our variable is v that we use. Unit is meters per second. And keywords are things like how fast are we going, final velocity, initial velocity. Our basic equation for finding it is, remember, this is just the slope of the position time graph, and it's just change in x over change in t. And now let's talk about instantaneous velocity. So the velocity at one particular instant. The only time we really care about this is when the velocity is changing. So if you look at our graph here of position and time, this is a curved position time graph, so we have acceleration. So that means our velocity is different at each point. Well, remember we learned a trick to find instantaneous velocity without using calculus by finding the average around a midpoint. Let's make our midpoint 2 seconds to find the velocity right there. So what we got to do is we just take an average velocity at 1 second to 3 seconds. So that way our midpoint is at 2. So if we do that, our position is at 9, and our initial position is at 1, and then our change in time is from 3 to 1. So when we crank that out and we get a velocity, we get 4 meters per second. So our velocity at 2 seconds is 4 meters per second. Cool. So moving on, acceleration. We were touching on this already. Our variable is a. Our units is, you can write it 2 ways, meters per second squared or meter per second. The whole idea of acceleration is a change in velocity over a certain amount of time, so speeding up and slowing down. Our basic equation is this is really just the equation version of what was written in the last bullet point, change in v over change in t. And for our purposes in this class, it is always going to be a constant. So we'll never get some funky equation. It's always going to be just a number, like 5 meters per second squared, and that's only going to be a constant. Okay, let's talk about graphs, because you guys have seen plenty of those. Before, what we did was what we have on the left, where we just have a constant velocity, because we know that that slope there is constant, so the velocity is constant. On the right, it's curved, so we know that there's an acceleration in some way, shape, or form. If it's curved, there's acceleration. And again, if it is going down, then we have some form of negative velocity. If it's going up, it has a positive velocity. Okay, different ways it can curve. All right, so easiest way to think about this, if it is concave up like this, then what we have here is a positive acceleration. So concave up, positive acceleration. Concave down, we have a negative acceleration. So if it's curving down, negative. If it's curving up, positive. Okay, now let's look a lot at velocity time graphs. They're very useful because you can find anything that you need to know from a velocity time graph if you know where to look. So on the left, what we have is a constant velocity, because it's a flat line. On the right, we have a changing velocity. So if you notice, we have a positive slope, so that means we have a positive acceleration, and it's a constant. If it's sloped down, we have a negative acceleration. Okay, now let's go into a little more detail with velocity and time. Things that we can find from a velocity time graph are things like acceleration, and we can find displacement. So if we find the area of this region right here, so this shape, then what we can find is displacement. You can do this a bunch of different ways, and we'll get to an example in a minute. And then if you find the slope of the line, find the slope of this line, that's acceleration. So let's do some more examples with graphs here. So how to get velocity and acceleration from a position time graph. The key thing here is to look at the slope. So if you want the velocity time graph, look at the slope of this graph and how it changes. So here's one example. We have something that's curving up. So we have a slope right here that's increasing. So if we have a slope that's increasing, then we have a positive constant slope on the velocity graph. And looking at the acceleration, we have a constant positive slope, so we have a constant positive acceleration. Well, what if it's curved down? So it's concave down. That means everything's going to be negative. So our velocity is decreasing, so we're going to have a negative slope. Now we have a negative constant. So concave down, we have a negative acceleration. We have a negative slope, then that means we have a negative acceleration. There's our negative acceleration. We have a negative constant acceleration. Okay, let's do an example with the most recent activity that we did with actually calculating these things. So from this graph we can calculate a couple of things. We can find our acceleration and we can find our displacement. So first thing is we're going to find our acceleration. So remember, it's just the slope. That's all we got to do. Find the slope. So we got our slope is just going to be our 10 minus 5 divided by 5 minus 0. Just taking the 2 points right there and right there to find our slope. And we get this, 1 meter per second per second. So every second it increases 1 meter per second. Okay, now we're going to find displacement 3 different ways. First way is we're just going to find the area. So we can break this up in a couple ways. The way I'm going to do it is find the area of this rectangle, and then I'm going to find the area of this triangle and add them together. So the first one right here, where I got 12.5 meters, that's the area of the rectangle. No, excuse me, triangle. The next one is the area of the rectangle. So if I add them together, then my displacement is this, 37.5. Alright, let's do it another way. Let's use an equation instead. I'm going to use this one because we know all the things in the equation. So if we assume this starts at 0, which you can, we can say that the x sub 0 is 0. So that'll make it simple. We know the initial velocity is 5. The time frame here is 5 seconds. We found the acceleration of 1, and then again our time is 5. So all I'm doing is plugging everything into this equation, plugging in the numbers I know. And if I crank that out, I get the same answer, 37.5 meters. Okay, just to convince you even farther, let's use a different equation and get the same result. Again, we know that velocity, and we know the acceleration. Then we can solve this for x. So here we go. I'm going to solve this equation for x and then plug my numbers in. If I plug all my numbers in, this is what we'll get. And, big surprise, we'll get 37.5 meters. Alrighty. Hopefully this video helps. If you want to get another good summary, tune back in Wednesday, Thursday. We'll be doing more practice of this in class. And I will see you guys then.